Now let's talk about the speed of sound in a medium. Remember what's a medium once again? It's filled with particles. It can be solid particles, liquid particles, or gas particles. Just pay attention that the speed of sound will be different in a different type of medium. So what this simply means is, if the sound is going to move through water, it's going to move at a specific speed. If the sound is going to move through air, it's going to move at a different speed. Now, just a quick recap of what sound waves are. Sound waves are an example of longitudinal waves, and then we know longitudinal waves needs a medium. Once again, if there's no medium, it means there will be no wave. And once again, sound waves, because they are longitudinal waves, you can see here in the illustration here at the bottom, this is the illustration of a longitudinal wave, so sound waves looks exactly the same. So let's look at let's call it the rules when it comes to the speed of sound in a medium. So what are the rules? The first one is, the closer particles are packed, the faster the sound will travel. So obviously the more packed they are, the closer they are to one another, the faster the sound is going to move. So obviously we can assume that in a solid, the sound is going to travel the fastest through because they are very, very close to one another. And then in a liquid, you can see the particles are a little bit spread out, which means the sound is still going to be fast, but just a little bit slower than solids. And then in a gas, you can see particles are very, very spread out, which means the sound will travel the slowest through the gas. And then over here you can see this represents a vacuum. A vacuum means there's no particles, and if there's no particles, we know a sound wave will not exist. So obviously in a vacuum, no sound is going to travel because there's no wave. And then the second rule, the higher the temperature is, the faster the speed of the sound will be. So let's say the speed or the sound is moving through water. If the water is obviously going to have a higher temperature, or if the water is hotter, it means the sound is going to travel faster. And if the water is colder, it means the sound is going to travel slower. And then the last rule, number 3, the more elastic a medium is, the faster the speed of the sound will be. So we know that the speed of sound is different in different type of mediums. So in this table here, you can see that the speed of sound when it's moving through air is 343 meters per second. If the sound is moving through water, it moves at a speed of 1,480 meters per second. And if it moves through steel, it moves at a speed of 6,000 meters per second. So once again, different types of medium, the speed of the sound will be different. So if they ask you a question, for example, calculate the frequency of the sound if the sound is moving through water. If they do not state that the speed of sound through water is 1,480 or 1,482 meters per second, if they do not state that, then you assume that the speed of sound through water is 1,480 meters per second. But let's say they've stated that the speed of sound through water is 1,483 meters per second, then you use the given value. So always remember, you memorize these values. If they do not give you the speed of the sound in that medium, you use these values. But if they do state the speed of the sound through that medium, then you use the given value. Now, let's look at how to calculate the speed of longitudinal waves. So the first formula that we can use is V, which is the wave speed or the speed of the wave measured in meters per second, is equal to the frequency times the wavelength. Frequency is always measured in hertz, while wavelength is always measured in meters. So pay special attention. If the wavelength is given in millimeters or centimeters, always convert back to meters. Then the second type of formula that we can use is V is equal to the change in distance, which is also measured in meters, over the change in time. The time is always measured in seconds. So you will see these two formulas are exactly the same as the transverse formulas, and that is because longitudinal waves and transverse waves are both mechanical waves. So therefore we can use the exact same formulas to calculate the speed of the waves. So let's look at a few examples on how to calculate the speed of a longitudinal wave. Okay, so let's quickly look at an exercise or an example on how to calculate the speed of a wave. What type of wave? The longitudinal wave. So they asked me to calculate the speed, so we know we need to calculate V. So what information do I have? So they have given me the total distance that this wave traveled, so I can see that delta X is equal to 6 meters. What else did they give me? They have given me the total time that it took this wave to complete a distance of 6 meters. So the change in time, delta T, was 1,5 seconds. What else did they give me? They've given me wavelength, but they did not give the value. But can I calculate the value? Yes, I can, because I know that wavelength is simply the length of one wave, meaning middle of a compression to the middle of the next compression. But I know that they've given me the total distance. So to get the length of one wave, I can simply take the total distance divided by the number of waves in here, and then I will get the distance of one wave. So wavelength is the total distance, divided by the number of waves. So then I'm simply going to substitute. The total distance was 6 meters, and then the number of waves, remember from where to where does a wavelength stretch in a longitudinal wave? It's from the middle of a compression to the middle of the next compression, or the middle of a rarefaction to the middle of the next rarefaction. So let's quickly count. So there's going to be 1, 2, 3 complete wavelengths. So there's 3. 6 divided by 3 is going to be equal to 2 meters. And there I have my wavelength. Now, what are the two formulas that I can use to calculate the speed of a longitudinal wave? There's obviously two formulas. The first one is V is equal to frequency times wavelength, or we can use frequency is equal to the change in distance over the change in time. But what formula am I going to use? I can use the second formula because I already have enough information. I do not have to calculate something extra. I can jump right into this one. So V is equal to the change in distance divided by the change in time. And then I'm simply going to substitute, which is 6 divided by my total distance, which is 1,5. And then I'm going to grab my calculator. 6 divided by 1.5 is going to give me an answer of 4 meters per second. And there I have my speed of the wave. If you used the first formula and you got to the answer of 4 meters per second, it will still be correct. I've just used the second formula because it's just a shorter version and it takes less time.